Okay, ladies and gentlemen, I would like to say welcome you all to our today's session. Luckily, we have a very famous professors today, so we'll have a very nice time. So let me introduce the first speaker of this morning session. Our first speaker is Professor Tony Sai. He is from University of Pennsylvania. He will talk on transcending data boundaries, transfer knowledge, and statistical learning. So please warmly welcome Professor Tony Sai.
Thank you. Yeah, first I want to thank the organizers for inviting me again. It's the uh, third international conference on basic science, and I have attended all three. So I hope I will continue to come. Where's my? Okay. So today I want to talk about some recent work on transfer learning. And I think AI is now the most often mentioned terminology in general press and also in academic research. It's almost everywhere. And AI as a subject uh, started in 1956 because that year, the summer of 1956, there was a conference held in Dartmouth College. And the goal of early AI, the original AI, was to prove theorems. Roughly speaking, the goal was to build a machine that can prove mathematical theorems that we humans cannot prove. And that effort, it focused on formal reasoning and automate theorem proving. And that effort lasts for 30 years. By the end of 1980s, it's generally agreed the whole effort has failed, totally failed. Even up to this point, 40 years later, we still have not able to use machine to prove any theorems that we humans cannot prove. But why AI is so fashionable or active now? Because the current AI is based on very different paradigm. It's driven by big data and statistical modeling and machine learning. And what's the key difference between the two? If it's formal reasoning, it has to be correct all the time. A implies B is true all the time. Cannot be 90% or 99%. It doesn't allow for any error. But we all know that if it's based on statistical or probabilistic model, we allow for error. And that makes a huge difference. And the new AI has been very successful. And it will continue to be very successful in the next few decades. By some forecast, it will change the way we live, work, and communicate. So it has been very tremendously successful and impactful. And that's driven by three key factors. Because by 1990s, we have internet, and that generates massive amount of data. And also, the computing power has improved significantly from 1950s, 60s, and up to this point. And certainly, statistical modeling and machine learning algorithm has improved dramatically over the last decades or so. And as statistician, I always want to mention, to quote Tom Sargent, in terms of statistics. And statistics, we all agree, it plays a very significant role in data-driven AI. But according to Tom Sargent, who won Nobel Prize in economics in 2011, he said, AI is actually statistics. It's not statistics is important for AI. AI is statistics, nothing else. I'm sure if you talk to computer scientists, they would disagree. But regardless, it means that statistics is important. So this AI has been around from the beginning for 70 years, over 70 years. But actually, we don't know what's exactly intelligence. We're talking about artificial intelligence. But what's exactly the definition of intelligence? And that turns out to be very difficult. And there's no universal definition of intelligence. I remember the first year I come for the international conference on basic science. And the lifetime achievement in mathematics was given to David Mumford, a Fields medalist, for his contribution to algebraic geometry. And by the time he went up to the podium to accept the award, the prize was $1 million US. So it's a very significant award. And he said, actually, I haven't touched algebraic geometry for over 30 years. For the last 3 decades, I have focused on my research in understanding the meaning of intelligence. So actually, we don't know what's exactly called intelligence. But one thing that's clear, the intelligence, a key feature of intelligence is the ability to learn from experience. If a person doesn't learn, keep making the same mistake over and over again, we would say the person is not intelligent. So we should be, a human has the natural ability to learn. Every day, actually, we encounter slightly different problems and in a slightly different settings. Life never repeats itself exactly the same. But based on what we learned before, we can adapt very quickly to a new setting. And that's a very powerful and very useful ability. So this ability to transfer knowledge from one task to another is essential for effective learning. And transfer learning basically is trying to mimic this ability of humans. It has been around for about a decade. It has been very successful. And the early work was mostly done by computer scientists. And they have proposed quite a few very useful methods for different problems, from computer vision to classification of image, speech, and everything else. Graphically, I think this graph illustrates the difference between traditional learning and transfer learning. In traditional learning, if we have one task, or you can think of this as one distribution, you draw a sample from this distribution, IID sample from this distribution, you try to learn the mean, variance, regression, classification, anything. And if you have another task or another distribution, you draw another IID sample and we learn. Basically, we learn one by one. And transfer learning, the idea is different. We have some samples from some task or some distribution that's similar to the target, but maybe different. And we try to learn from those samples and help us to make inference or estimation for the target distribution. So it's more general. And the other applications, for example, in large language model, a key technique, one of the key techniques is transfer learning. One example is language translation. Suppose you learned one language very well. How can you utilize that knowledge to learn another similar language well? And humans can do that. I'm sure if you're an English speaker, you can learn French more easily. But can we train a machine to do that. So transfer learning is very useful and, in large language models. And also during COVID, COVID is a worldwide epidemic. At that time, every country or every region wants to know what's going to happen, try to model the trend of COVID. And the question is, can we utilize the knowledge or the data from other regions to help us make a prediction more accurately? And in medical applications, we want to know, for example, whether a certain individual is likely to develop cancer or not. And so you want to study a cancer, but you also have data from patients with other diseases, other cancers. Can you utilize the data or knowledge to learn this cancer more accurately? And there's no shortage of examples. And the conventional learning, as I mentioned earlier, if you have population, you take a sample, and you get your data, and then you make inference. If you have another population, you do exactly the same. So transfer learning asks the question, can we learn from the data drawn from another distribution for the purpose of understanding another, say, population Q? And that's exactly the goal of transfer learning. So in transfer learning, we want to transfer knowledge from other distributions or other samples. And the question, in general, of course, it could be multiple, not just one source data, but multiple source data sets from different distributions, P1, P2, all the way to PM. And we want to make, but the difference here is that our primary goal is still about this distribution Q. We are not interested in those distributions P1 through PM. And I will mention at the end, this framework is different from federated learning. So here are some fundamental questions. First of all, the usefulness of the sample drawn from population P depends on the similarity between the two distributions. If those distributions have nothing to do with each other, then there's no reason why their sample is useful. So given that there are some similarities between source and target, the question is how much knowledge can be transferred? How useful is the sample from population P for the task under population Q? Two is that how to build an algorithm or how to optimally transfer the knowledge from P to Q. And transfer learning has been very successful, as I mentioned, in applications, in many machine learning applications. But the early work doesn't really focus on theoretical understanding of the problem. It's more about methodology. So in statistics, it has drawn increasing attention in the last few years for different problems. And for non-parametric classification, linear regression, and actually, essentially, any statistical problem has a version under transfer learning. You just ask yourself, what if you have an additional data set? Or what if you have other data sets? Can those data sets be used to help solve your problem, whatever their problem is, whether it's classification, testing, anything? And so today we are going to mainly focus on non-parametric classification. But let me first give some examples. Say high-dimensional linear regression. In high-dimensional linear regression, the problem has been studied for a long time. And it's a linear model, and you have x, y pairs, and you want to estimate this beta well. And the problem is very well known in classical setting. Lasso is known for solving this type of problem. But in transfer learning, in addition to that linear model, we have a collection of other linear models. We have we have linear models, additional XY pairs, and under the assumption if the regression coefficients are similar to each other, the question is, can you help estimating beta by using the additional source data? So the question is, can the source data be helpful for estimating beta? We are not interested in those omegas. And the second question is how. And this is a supervised version. And it could be unsupervised. For example, Gaussian graphical model. And if we only have data from the target, that's a classical problem. We want to estimate the inverse of the covariance matrix, the precision matrix. From there, we can construct a graph. But now, under transfer learning setting, we have source data from other distributions that are related, but they're different. And again, you ask exactly the same question. But today we are going to focus on non-parametric classification. So in non-parametric classification, it's very similar to regression, except the response Y is binary, is discrete. So we focus on binary classification. So Y is either 0 or 1. And the goal is, of course, is try to predict the label based on the covariance. And what's different is, in addition to the target data, we also have source data from other distributions. And for that, we need to mix. There are two different paradigms under this framework in transfer learning. So we need to define the relationship between P and Q. And there are two main paradigms. One is called covariate shift. Another is called posterior drift. Covariate shift means that the marginal distribution of x's are different, but the conditional distributions are the same. Y given x is the same between P and Q, but the marginal distributions are different. You can imagine this type of situation occurs when the same study you run, say, clinical trial, say one in the US, one in China. The population characteristics are different, but the conditional, given x, say how likely you are going to get cancer is the same. And another is posterior drift, where the marginal distributions are the same, but the conditional distributions are different. And this can occur, for example, in crowdsourcing. And you have experts who are much more knowledgeable. The conditional distribution is much different, but the marginal distribution is the same. And today we are going to focus on the second one, posterior drift. And other people have done work on covariate shift. So under posterior drift model, the marginal distributions are the same, but the conditional distributions are different because Y is binary. A critical quantity to understand the classification problem is this regression function or the conditional distribution given Y equal to 1 given X. Because if this quantity is known, then classification becomes trivial. If this probability is more than a half, you always guess 1. If it's less than a half, you guess 0. You always take the one with higher probability. It's like betting on the outcome of some coin toss. If you know the probability of heads, you know how to bet. And we have two quantities, eta p and eta q. And the key to relate p and q, the two distributions, is to define the relationship between eta p and eta q. And the base classifier under q, if you know eta q, you don't really need anything else. That's the optimal classifier. But of course, in real life, we only observe data, and we don't have any knowledge about this eta. So the question is how to define the relationship between eta p and eta q so that it's feasible to characterize the knowledge transfer between p and q. And that quantity, so that's an illustration of this eta x. And the quantity that characterizes the relationship. So So we make one assumption: the base classifier and the covariance distribution stay the same, but under the posterior drift model, we have this quantity called transfer exponent. And this eta is very important. This gamma, the exponent, is very important. We will not have, I don't have time to get into the details of this gamma, but I do want to mention that the smaller this gamma is, the more useful the data from P distribution is for the classification and the Q. And this will show up in the optimal rate. So this gamma relates the classification difficulty of this source data with the target. And we also need some regularity conditions. These regularity conditions are just very generic. It's not unique to this transfer learning problem. For example, that's holder space, holder smoothness, and this margin class, this only concerns Q. So even in classical classification problem, we have this exponent alpha. And you don't need to remember any of this. I just want to show you very briefly that the difficulty of the problem depends on the smoothness and also depends on the margin condition. But these quantities also appear in classical classification problems. And the performance of a classifier, is quantified by this excess risk. Because even you have the full knowledge of the eta function, you're still going to make a mistake. Nothing is better than the base classifier. So for any data-driven method, how good is the method is quantified by this excess risk. How much worse than the base classifier? So we want to understand first the minimax excess risk. So what's the best way of transferring knowledge from P to Q? But so far, we have not talked about any constraint. And diverse data source is certainly one characteristic of modern data analysis. But in modern data analysis, there's something else that's of paramount importance. That's privacy. And the amount of data we generate now in a single day is more than all the humans that generate from the beginning of the time until maybe year 2000. So the data is exploding. It's increasing exponentially. And with that, there's major concern about privacy. If the government wants to know where we have been, as long as you carry your cell phone, they can easily find out. We are here, and we stay here for how long, and they know. And the question is, can we do something to protect privacy? And there are several questions related to privacy. One is how to preserve privacy. And two is how to optimally balance the statistical accuracy and the privacy in data analysis. So let's do a very simple thought process. If there's for any statistical problem, if there's no constraint, we can choose the best statistical procedure to do it. And that procedure may or may not protect privacy. But now we say we want privacy. So we are no longer allowed to choose among all possible methods. We can only choose from a small subset of methods that protect privacy. So the performance of those methods will not be as good. So the question is, how much worse? And this kind of problem arises in a wide range of applications. One is like healthcare. If you want to start healthcare, where do you get your data from? You get your data from hospitals. And the hospitals have obligations to their patients. They cannot disclose their patients, violate their patients' privacy. But hospitals also have common goals. For example, they all want to understand, say, to improve the use of healthcare monitoring, or they all want to understand certain disease. So they want to solve a problem, but they also have constraints. And the question is, can we do statistical inference under those privacy constraints? And it's impossible nowadays if you want to study, say, healthcare, and you use a USB and take a copy from one hospital, then take another copy from another hospital. That's impossible. And same is true in banking. All the banks, they want to find the best way to detect, say, financial fraud, because banks don't want to be cheated. But they also have obligation to their clients, their customers. So the question is, can they collaborate to learn something under the constraints that protect their customers' privacy? And here, for different hospitals and different banks, they have different levels of privacy requirements. So it's very heterogeneous. And it can also be social media, for example, or the social media platform. They also want to develop the optimal, optimal personalized and targeted ads. Each platform has their own data, and the question is, can they somehow collaborate to train the best possible model without violating their customers' privacy? So there are lots of examples of this type. So far, I have focused on the framework. And to me, the framework is more important than specific problem that I'm going to discuss. So today, I'm going to talk about classification in detail. So it's a joint work with my former postdoc, Anab Audi, who is now at Ohio State, and my PhD student, Abhinav. So we can think of this as a very simple example. Say we want to do disease prediction. Does a patient have heart disease? How do we determine a patient is likely to have heart disease? We collect data. So we collect covariates, age, BMI, smoking, chest pain, and anything that you can measure. And we have patients. We have patients across different hospitals. Say some in US and one in Switzerland, one in Hungary, and they're different. They're heterogeneous, and in terms of the patient's characteristics, and they're also heterogeneous in terms of sample size and many other aspects. But the basic indicators of heart disease are universal, whether you live in the US or you live in Switzerland. And the goal is to improve target classification accuracy. Suppose you work in Cleveland, and your main target is for the population, say, here, but you also have data from other hospitals elsewhere. And the question is, can we improve the target classification accuracy under the constraints that the patient's privacy is preserved? So graphically, we have hospitals here. We want to transfer the knowledge of data drawn from this hospital under the privacy constraint to help classification for the other hospital. And I have shown this to you before, but now we have an additional constraint. The additional constraint is we require a privacy guarantee for all the patients from the source data. And the problem is difficult and complicated. But before we go any further, we still need to understand this notion of privacy. So what's exactly privacy? Just like intelligence. But intelligence is a harder question. Privacy is slightly easier, because in abstract, we all know what's privacy. Basically, I don't want you to know what I have done. I want to hide myself from the rest of the population. But mathematical definition turns out to be difficult. and there are no universal definition of privacy. The two primary one. One is called differential privacy, which we will use today, but there are also other notions of privacy like local privacy. And privacy has been around and widely used. So DP itself, as a concept, is very simple. It's a concept of protecting the information of any single individual from the released information. So any data you publish, based on that, you cannot tell who is in the sample, who is not in the sample. And that protects the privacy of the subjects. And DP has been widely used nowadays by all the high-tech companies in the US. And one of my students is working at Amazon. Every day he's developing algorithm, privacy guaranteed algorithm for Amazon. And DP, the most important significant application was used in the latest 2020 US Census. Because all the previous US Census is carried out every 10 years, every decade. And all the previous one, they publish aggregate data. For example, the median income, age, or anything. But then they realized that that does not protect privacy of the population. So since 2020, all the published data guarantees privacy. So here's a definition, mathematical definition of differential privacy. Conceptually, it's easy to understand. It's almost like robustness in statistics. But the exact definition is as follows. So suppose you have two data sets, or you have one data set, consists of n people, n subjects. If you replace any one of them by another subject, so you have two data sets. They are identical except one person. Then if you publish a statistic called M, whether it's a sample mean or anything, you publish a statistic. If this statistic is not sensitive to the replacement, basically statistically you cannot tell whether that patient or that person is in the sample or not in the sample. Because if you replace this person by another person, you couldn't tell. And that's the mathematical definition. And there are two parameters, one called epsilon, one called delta. And epsilon quantifies any single individual's influence on the statistic. It's sort of like likelihood ratio, log likelihood ratio. And this delta is the probability that this bound fails. And typically, delta is very small. Delta is n to some power. And what's important is that to guarantee privacy, you cannot simply, for example, anonymize data. Think about patient data. Imagine patient data is summarized in, say, an Excel form. The first column is patient's name, right? The second column is the patient's ID. And the third column is the heart rate or whatever clinical data. Then we all know to guarantee privacy, we should not publish the first column. We should remove the name. And we should certainly remove the ID. Then the rest looks all very similar. We should publish that, anonymize the data. And that's not nearly enough. The well-known example that some of you who are old enough remember that back in 2006 to 2009, there was very famous competition, Netflix competition. It only ran once. The reason it only ran once was people found a way to identify the customers that's published by Netflix after they anonymize the data. So if you simply remove the name and ID, it's not enough. And if you simply publish, for example, Z-bar, the summary statistics, say, instead of, say, publish the individual household income. You just publish the average for the region. It's not enough. So we need to do something more sophisticated than anonymizing data or publishing summary statistics. But turns out to guarantee privacy, it's not difficult. If you just want to have privacy, you simply add random noise. If you publish, say, sample mean, you add additional noise to it. You can easily imagine if you add enough noise, it's a piece of junk. No one can tell. But as statistician, we know that that's not good. Adding noise is not good. So adding random noise downgrades statistical accuracy. We are still interested in making statistical inference. Here's one well-known example. So in image classification, there's a well-known test data set called CIFAR-10. If we don't have any privacy requirement, the best known algorithm can achieve 90% accuracy. They can classify the image 90% accuracy. But with privacy, even with epsilon as large as 8, the best algorithm achieves 65% accuracy. So the difference is huge, 25%. Now the question is, why? Maybe because we are not smart enough. There's another algorithm that we don't know yet. It guarantees privacy and also achieve much better accuracy. Or maybe that's the best we can do. So the question is, what's exactly the cost of privacy? So we are going to continue the questions I showed you earlier, right, about transfer learning. But now we have one additional question: how to quantify the cost of privacy in terms of statistical accuracy in transfer learning. And our eventual goal is to develop efficient algorithm that optimally transfer knowledge while ensuring privacy. So now back to the real problem. In the real problem, we have IID samples from distribution P, we have IID samples from distribution Q, and we want to utilize the knowledge from the source data to help us do classification for the target. So S is for the source, and T is for the target. And because we have two, we are going to use a kernel method. So we construct those two functions, and to determine whether for a given X, it belongs to class 1 or it belongs to class 0, what we do is we make a linear combination of the two functions. If we only have one, we just use this function to do the classification. So for anyone who has done any work on kernel estimation, you know what's important. This H, the bandwidth, is very important. And kernel is somewhat important, but it's not very important. But now we have another quantity called W, the weight, is also important. But bear with me for 1 second. So assuming we know how to choose H and how to choose W, and that's the classifier we build. Of course, I mentioned earlier, we could have multiple sources. We have M sources. If we have M sources, we have multiple functions of this type from each source data. So what we do is we have a convex combination, a linear combination of those functions. If we choose the weights correctly, this will be good. But at least the classifier is of this form. But that classifier, this classifier does not guarantee privacy. So to guarantee privacy, what we need to do is we need to add noise. We are going to add noise to the target and add noise to the source independently. For a given X, we add just IID Gaussian noise, just univariate normal variables. But here, because x is a variable, it's a function, so we are going to add a correlated Gaussian process. And those the independent Gaussian processes, but with covariate kernel. So basically, we add noise individually to each component, to each source function and each target function. And I'm going to consider a special case. In the paper, we consider a general case because imagine if it's a hospital, different hospitals should have different sample sizes. And different hospitals have different levels of privacy requirements. Epsilons will be different. And also the gamma will be different. But the general case actually doesn't have an explicit formula. The general case, the rate is determined by a solution to an equation, so it's more complicated. So we are going to consider a homogeneous case. In this homogeneous case, the minimax access risk is given by this expression. So I need to explain this. It has 4 terms. Let's ignore this L first. L is a log term. So let's ignore this. Then we have 4 terms. Or separately, we have 2 terms because it's a sum. But within each, we have 2 terms. We have those two. Those two, one is determined even without any privacy. This has no epsilon, no delta in it. So even without any privacy requirements, and we only use target data, that's the rate of convergence. And the second one is determined by the privacy requirement. And then we have m times n is the total number of data points. So total number of total sample size. And this is the privacy requirement for the source data. It looks complicated, so let me. Oh yeah, that should be this should be a max. Yeah, thank you. Yeah, that should be a max. Let me think. No. D grade because I have a minus sign outside. So the smaller, the larger, because the exponent, negative sign there. Yeah. So, but your intuition is correct. So let's look at some special cases to understand this rate. Suppose there's no source data, so you only have the target. So that's a classical setting, but with privacy guarantee. Then the minimax rate. This is new. No one studied this problem before. Under privacy, the rate is determined by this. You can see that when the privacy requirements, when this epsilon 0 is large, so you don't care too much privacy, then the cost of privacy is not significant. The rate is still determined by the statistical error. But if you make that epsilon very small, in other words, you want very high level of privacy, fine, you will get privacy. But your classifier will be not nearly as good as before. So it will cost you significantly in terms of accuracy. And so that's for the case when there's no, alpha is the smoothness. Alpha is the smoothness of eta. Yeah. And another special case is when the privacy requirements are stringent. It's very are not stringent. So in other words, that we don't care too much about the privacy for the source data. Then we get this rate, and this rate is known A few years ago, in 2021, I worked with a former PhD student. We studied the transfer learning for non-parametric classification without privacy. And that's the rate. So in other words, the rate that looks complicated here, it covers a range of special cases. Now, let's think a little bit more about those four terms, because we have four terms, and we need to know when, which term is dominant. And we will look at this very quickly. It's somewhat interesting. It's not continuous. So on this plot, this is the log access risk, and that's epsilon. As you vary this epsilon, in other words, you vary the privacy level, you can see that sometimes this is a source with privacy. This is dominant. And then it's driven by some other factor. And then it comes back again. So it's not linear or not contiguous. And the picture is complicated, so I don't want to spend too much time to explain. But the key is that you can look at those four terms and try to decide when, say, the first term is dominant, when the second term is dominant, when the third one is dominant, and so on. So the cost of privacy can be very significant when epsilon is small. Let's think a little bit more about the practical issue. Earlier, I mentioned that H and the weight W. Those are important. And the previous theorem assumes we choose the best H and best W. But in practice, of course, we don't know how to choose, because those optimal choice depends on alpha, beta, and gamma. Just like in classical non-parametric regression, if you know the smoothness, the problem is easy. You know how to choose bandwidth, you get the optimal estimate. But how do you know those? You don't. And turns out that it's possible to come up, basically use Levsky's method, use a data-dependent method to search for the best value on a grade. And we have an algorithm that looks complicated. I'm not going to explain in detail, but basically you choose the H by minimizing some quantity. And you choose the best weight by looking at this. You can think of this as a signal-to-noise ratio. You want to choose the best W to maximize the signal-to-noise ratio. And the details are given in the paper. And we did some simulation to verify our intuition or to collaborate with the theoretical results. So here, the data-driven method is what's called adapt DTK. So that's the purple line. And the purple line, because it's a kernel method, so it also depends on the choice of kernel. So we have three different kernels. The Gaussian kernel, none means the flat kernel, and then triangle kernel. And there are some differences, but by and large, they are similar to each other. And this DTK is the optimal one, assuming we know how to choose the best H and W. So that's good. And this DT histogram, that's sort of using a naive method, and that's bad. And we also apply this to analyze the hard data I mentioned briefly in the beginning. And overall, it's quite good. And the best one is this one, adapt sample. Yeah, unfortunately, we use different names in different settings. So I think the framework itself, as I mentioned, is not unique to classification or any specific problem. You can embed any statistical problem under transfer learning framework. And you ask the question, what's the optimal performance? But transfer learning itself is also a special case of a more general setting called multi-source learning. And as I mentioned earlier, now there are many applications where data is not in a single place, or you have multiple data sets. And transfer learning is one such problem, where you have one data set of primary interest, and you want to borrow information from other data sets to help you analyze the data set of primary interest. And there are also another problem of similar fashion is called federated learning. And in federated learning, it's different. You also have multiple data sources. Think of, say, you have a collection of health organizations or hospitals. They have a common goal of, say, understanding a given disease. So this is one nice plot to illustrate. So you have data from a community hospital. You have data from a research center. You have data from a cancer treatment center. So you have multiple data sets. They all want to understand, say, how to treat breast cancer. But they all have obligations to protect the privacy of their patients. So what you can do is they allow you to train your model. So you can train a local model. Think of linear regression. You run your linear regression, you get your beta hat. But you cannot take that beta hat with you because they require privacy. So you have to do something, for example, adding noise to your output. And then you can take that privacy-protected output back to your office. And you do exactly the same for this hospital back to your office. And so you have, at the end of the day, you have a collection of outputs that protects the privacy of all the patients in different hospitals. And then you aggregate. You do something to those outputs, construct a final estimate, whether it's classification or regression or anything else. And the problem is very interesting and very important. If you look at the publication in federated learning, it's like exponential curve. And it's a very interesting problem statistically to understand what's the optimal way to estimate, to come up with the best estimate or classify as the end. And the reason I mention is that naive method doesn't work. Naive method means that for each hospital, you run your lasso or anything, you get your best output, best estimate. Then say you get a collection of estimates, you take weighted average or you just take simple average. It doesn't work. It turns out that in order for the final estimate to be optimal, the output from each source should be suboptimal, meaning that learning together is different from learning all by yourself. Think about taking an exam. If you take an exam individually, then each student should try their best. But if you take the exam together, so you have a collection of problems and you want to solve collaboratively, it turns out you should divide up. So it's a very interesting problem, and there are lots of recent publications on federated learning. And in addition to federated learning, there's something else I don't want to explain. So the key point is, with the rise of big data and so-called AI, now we have lots of new problems to solve, and they're all very interesting. So for federated learning, I just want to show you very briefly in terms of statistical framework. So you have different hospitals. You have patients' data. And what's common is the theta. So you have different distributions. They have some common objectives called theta. So they all want to learn this theta together. And you can analyze each one of them, and you can take away a transcript. This is called transcript. And the different requirements, whether it's privacy or communication, you take this transcript. At the end of the day, you want to construct an estimate that's a function of those transcripts. And, and your goal is try to make this data head as good as you can. So let me summarize. So today I focus on transfer learning with distributed DP constraints. And we study the classification problem, and we get the minimax rate of convergence, and also we propose a rate optimal adaptive estimate or classifier. And what I showed you on the slide is a homogeneous case. The sample sizes are the same, epsilons are the same, because that I can show you a formula. But in the paper, we consider the heterogeneous case, the diverse sample size and different privacy parameters, and also data they are heterogeneous across different servers. So if you are interested, you can look up this paper. And before we do this project, I have done a few problems on the transfer learning framework, and those without privacy. So with that, I stop. Thank you.
Thank you, Professor, for very nice talk. Any question for Professor, please?
Yeah, it's a great talk. Learned a lot. And my question here is, in some sense, so you didn't talk about choice of M. How many source data you
That's
combine?
typically given. M, most of the time, M is given.
Yes. I'm thinking about something slightly different, where it's like a measurement error problem. I do need to combine the classical one. I need to at least combine two different samples to be able to recover and identify some, say, the condition probability, those kind of stuff. So I wonder whether or not they have some similar thing. Basically, also say.
I don't know whether those problems are the same, because in the setting I'm considering, M is given. Think about, say, you study a disease, right? You have a certain number of hospitals.
In privacy, if you want to get more data, you have to pay. So if
Okay.
you have to,
That's why you are in economics department. You have to pay. We get data for free. Just joking.
So that's how I was thinking about what's the name of that.
But there's one thing that I didn't discuss, which is tricky one, is that it is a selection of source data. Because some hospitals are similar, but some hospitals are different. So it's like variable selection in classical statistics.
Okay, very nice talk. So I have maybe a couple of questions. So first, when you try to relate the source and target data, you have the condition, right? Along half, right? So if you insist just one formulation, that may not be, the best in some applications, right? So that requirement, you have a gamma parameter. So maybe it's possible, in different regions you have gamma.
It's possible you can come up with
better,
a
right?
different way to relate P with Q.
Right.
That's true, the source and data. And like in classical statistics, people figure out smoothness is a key. It determines the rate of convergence. But of course, you can also use some other structural assumption. For example, say a function is piecewise linear with many pieces. And that will show different types of behavior.
So maybe more closer to reality in some applications, right? So
that's possible.
Okay. So another question is that for the example you mentioned, real data, right, without privacy requirement, then you can get accuracy 90%. And if you insist, privacy, then down to 60-some%. So privacy. Earlier in your definition, you are releasing something. So in this, for this specific example, so
You also release the classification.
Reducing the
Yeah,
classification
the
probability.
classification. Yeah, the not the probability. The
It's 0, 1.
classification 0, 1.
Oh, I see. I see.
Yeah,
Okay. So,
that disclose the privacy.
I see. Okay.
Yeah.
All right. So now it's clear. Okay. Thank you.
Professor, I have a couple of questions. My first question is about for the single source classification algorithm. We have used the Rosenberg kernel. Did you think about using positive defined kernels working on reproducing kernel interspaces and or others regression classification algorithms?
Yeah, in this paper I mentioned, without privacy, in this paper we use nearest neighbor. The specific method is less important. You don't have to use kernel. You can use any other classification method, but as long as you privatize that method, it's fine.
Okay. My second question is for the multiple source case. If the number of sources is very big, and is it possible, I mean, to consider these as copies of random process and use linear function regressions model?
That's a very good question. In OR setting, we can consider large M, but not growing M. But I understand. Let me go back to the previous, not this one.
Because in this case, the data is huge. So
yeah, it's possible that there are some applications that M is very large, many groups of data, and each data source is small. Each set has only a very small number of data points. That's called meta learning, and that's a very interesting setting, but it's not what we consider. We consider each group has enough data points so we can construct a reasonably good classifier. And in the most extreme case, you can even think of one data point as one group. And then we need to develop different method.
Thank you.
All right. Maybe we are running out of time. Let me give one chance and you can discuss private.
Yeah, thank you, Professor. And I noticed you use Nevsky method to achieve adaptation. So we know there is other methods such as CV cross validation or some model aggregation method can also achieve adaptation. But based on my knowledge, a significant feature of Nevsky method compared to CV is that it can achieve point-wise adaptation. It can adapt to local smoothness. So in your context, does this mean that to achieve adaptation or to construct upper bound, you need some kind of point-wise upper bound. So you must use Nevsky method.
Not really. Our goal is not to achieve, at least in this paper, achieve local adaptivity. We could. For example, instead of this access risk overall, we can have a given X. We just want to classify this given X optimally. Then it's a local objective. To me, that whether use cross-validation or Leipzig method or any other method, in terms of big picture, it's less important. It depends on your personal choice. You can use other method. If you prefer, you can use cross-validation or any other method. As long as it works, it's fine. Just like the choice of kernel.
Thanks, Professor, for a wonderful talk. And I have two questions. The first is about the assumption that you assume that the covariate distribution of P and Q is the same.
Yeah.
But how to justify this assumption, especially when there's privacy constraint?
Privacy constraint has nothing to do with the marginal distribution being the same. It's more about the setting of the problem. It's whether the two populations in terms of X, the covariance, has similar characteristics. If you have two different countries, or say your one population is for male, another population is for female, then it would be unreasonable to assume the X distributions are the same. Then the covariance shift model is more reasonable. So it depends on the background of the problem. Different countries, yes, yeah. But you need to assume one of the two. Yeah, we have been thinking about whether we can relax that, because if they're totally different, then yeah, you cannot formulate the problem properly.
Thank you. And my second question is about the minimax rate. And I noticed that the privacy budget, epsilon delta, I don't find the delta in the result.
That's a very good question. In all the known results, delta does not show up, mainly does not show up in the lower bound. It's in the upper bound. That's why there's an L there. There's a gap in the analysis of log term here. This ln is log of delta, but we don't know whether it must be there or it shouldn't be there. The lower bound does not have delta. The upper bound has delta in it. So it's a very a good question, and also it's a very good problem for research. Yeah, how to characterize the dependence on delta, but it's very difficult, because I have written a few other papers on privacy. And yeah, only in very special case, we have the exact rate.
Yeah. And also, its the result depend on the non-random, the choice of weight.
We have the adaptive version of this result.
Oh, okay.
Basically, you get the same result, but with this L, that's different. The log term under the adaptive setting is slightly larger. Yeah, otherwise we get exactly the same rate.
Okay, thank you. Thank you so much.
Okay, please let's thank Professor Tony for such a wonderful talk. And it will be a tea break. Can you thank Professor, please? Clap. Yeah.